Okay, so we are starting now. Okay, so welcome everyone. Today we're going to talk about Gauss' law. It is a really basic and really useful thing in the whole electricity. Okay, so first we'll have a quick review on electric field and electric field lines. So as we all know, electric field is like a central element in the electricity because a lot of important variables have formulas relating to electric field. And here are some formulas that I'm pretty familiar about. And about electric field lines. Hopefully you already know something about that. It's basically, it can represent the magnitude and the direction of the electric field. So for example, if I have these arrows representing the electric field, these are the electric field lines, right? So this means the electric field is pointing right, and how dense this electric field lines are represent how big the magnitude the electric field is. So for example, if I draw like this means the electric field in this part is bigger than the electric field in this part, because in this part, the electric field lines are more dense than the downward part. Okay, so we will move on to electric flux. This is probably a new concept and it's really central to Gauss' law. It basically means how many electric field lines pass through a given area. So I will further interpret this definition. So we draw a plane here. And for example, there's the electric field passing through it. And we can first assume that the electric field is uniform. Then according to the definition, it means how many electric field lines pass through a given area. And that's the function mentioned here. You can see that this represents electric flux. It equals to E, the magnitude of our electric field times the area, S. S means the area of this yellow area. However, this formula is often not this simple because, as you can see, sometimes they have a E times S times cosine theta. So where does this cosine theta come from? So, for example, our plane tilted in this way. It tilted with an angle of theta. Then our formula, this formula can't be applied because this plane is tilted. And what we can do now is we project this orange plane onto the plane that is perpendicular to the electric field. So as I draw here, we project it to this plane. And so now this blue area is equivalent to the orange area. So this blue area obviously equals to S times cosine theta. So in this case, the electric flux equals to E times S times cosine theta. And if some of you have learned more about work and energy, this is kind of similar to work equals to F times X. And if they are not in the same direction, we have to times cosine theta, right? So F is this and X is this. This is a more famous formula. And also, if some of you have learned more about vectors, you can also interpret it, this electric flux as the vector E dot product the vector S. And if you haven't learned about vectors, it is fine because we won't use this formula anyways today. Okay. So now we consider another circumstance. This is kind of like the concept of calculus, but don't be afraid. It's fine. It's pretty simple. So we have this shape. It's like a hat, right? And there are electric field lines passing through it. These arrows represent electric field lines. And we want to know the electric flux throughout this orange area. So how can we calculate it? Since this is not like a plane anymore. So what we do is for example, we take a small part on this area. And for example, we call it delta S. And then there's a small amount of electric lines passing through it. We call it delta E. So basically, for this orange area, the electric flux equals to delta E times delta S, or possibly we should times the cosine theta. So for the whole orange thing, it equals to every part. Like we take a small part here, we take a small part here, we take a small part everywhere. So this means sigma. So the sum of every area times the electric field at that specific point. And this is not really that important today. So if you don't understand it, it's fine. Okay, so now let's consider a point charge. This is more simple. So here's a point charge of Q. And it emits, as we all know, it emits electric field lines like this, right? Then, for example, now we draw an orange circle around it. And actually, this orange circle is actually a sphere in the 3D dimension. So now we want to calculate the electric flux on this orange sphere, the surface of the sphere. So we still use our formula, right? Electric flux equals to E times S times cosine theta. And now cosine theta looks really annoying, right? Yeah, I hate trigonometry. So let's try to get rid of it. First, let's think, do we actually have to consider theta? You can see that, for example, at this point, the electric field lines is pointing this way, while the surface area is this way, right? The orange. They are perfectly perpendicular since this electric field lines come from the center, comes from Q. And this circle has center at Q. Yeah, I forgot to mention, sorry. So, which means theta equals 0. So if you don't know that the area, the vector area, it points perpendicular to the surface area, so theta equals 0. It's the same to the this yellow and green plane in the first example, right? So basically cosine theta equals to 1. So we can cancel this out. So it only equals to E times S. Okay, so now everything seems to become easier. So for example, if we say this surface, this sphere has a radius of R, then we can plug in everything. E, as we all know, equals to K times Q over R squared, right? For at this point and this point, everywhere, E equals to this thing. And then S is the surface area of a sphere, which equals to 4 pi R squared. Okay, now some interesting thing happens, right? We can cancel out this R squared, and what we are left is 4 pi KQ. So this is a really interesting formula because it is independent on R, right? It doesn't have to do with R, which means the distance from our central electric charge. So why this happens? Now, if we draw another sphere, a green sphere that has a bigger radius, for example, its radius is R prime. Then for the for the green sphere, its electric flux still equals to 4 pi kq, right? Since we already said it doesn't have anything to do with R. So does this make any sense, since it is a bigger sphere, but the electric flux is the same? So the reason is, as you can see, we from the definition we said electric flux means how many electric field lines, how many pass through the given area. So for the orange area, there's 1, 2, 3, 4, 5, 6, 5, 6, 7, 8 white electric field lines passing through this orange surface, right? And now for the green sphere, the green area, we still has 1, 2, 3, 4, 5, 6, 7, 8 white electric field lines passing through the green area. So for both areas, there are 8 electric field lines passing through. This means the electric flux should be the same. Okay. So okay, now we can still do more thing to this formula. In case you don't know, we have a formula called K, which means the K here, the K we usually use. K equals to 1 over 4 pi epsilon 0. Epsilon 0 means vacuum permittivity. It is a constant, equals to 8.85 times 10 to the negative 12, but you don't have to care about it. You just know that it is a constant. So now we can substitute this K into our formula. So this gives electric flux equals to 4 pi times 1 over 4 pi epsilon 0 times Q. The 4 pi cancels out. So this gives us Q over epsilon 0. This is a really, really clean formula, right? Okay, so now we have the formula that for a point charge, if we circle it with some area, its electric flux always equals to Q over epsilon 0. And we can see that if we do something strange, for example, we draw a ellipse shape area, this formula should still apply, and we will explain it later. Okay. So now we can introduce our famous Gauss law. So this is the formula. This is actually the formula that we just derived over there. And although this formula seems to only apply to a point charge, it actually applies to everything, and I will explain it later. Okay, so several things to be aware of this formula. This S means area, right? This area have to be enclosed, meaning that it is like a sphere or a surface of a cube, or your water bottle with a lid. It can't be like a water bottle without a lid. So for example, this is your water bottle, and this part doesn't have anything at all. This thing, you don't have a lid on it. This is not counted as an enclosed area. It have to be an enclosed area. This is very important. Okay, so why this formula works? We can use the thing we derived here. So we already know for a point charge, the electric flux equals to E times S equals to Q over epsilon 0, right? And why does this apply to everything? Now we have a bit more complicated example. For example, there are two charges, Q1 and Q2. And they are fixed and they are kind of independent, right? So each of them emits electric field lines. Q2 also emits electric field lines. And although we know that the electric field here is not equal to this line because it is we have to add the electric field lines by Q1 and Q2, but now we can just interpret it as take Q1 and Q2 independently. And we have this yellow surface area chosen. So for Q1, we already know that it emits electric field lines and passing through this yellow area equals to Q1 over epsilon 0. And for Q2, its electric field lines also pass through this area, and it have a magnitude of Q2 over epsilon 0. So if we now we consider Q1 and Q2 together, and we want to find how many electric field lines that pass through this green area contributed to both Q1 and Q2. So we can simply just add them up. This equals to Q1 plus Q2 over epsilon 0, which equals to the net charge over epsilon 0. Yeah, and I forgot to mention this Q doesn't mean that, like, if you have a Q3 here, the electric flux doesn't count Q3 because it is outside this yellow area. This Q means everything enclosed by this surface area. So now we've proven that for Q1 and Q2, if there are two charges, our formula here still works. So now we can conclude that if we have almost infinite charges, right, inside, or if, like, here is a cube full of charge, but its net charge is, for example, Q cube, and then here's Merrick, here's me. I'm also full of charge, and I have a net charge of Qm. Then the electric flux passing through our yellow area equals to Q1 plus Q2 plus Q4 plus just plus everything inside our given area and divided by 0, right? Okay, so now hopefully you get a brief concept of this formula, Gauss law. Again, the thing to be aware of is this S have to be an enclosed area, and this Q have to be the net charge, the accumulation of every charge enclosed by our surface, right? Okay. So now we can go deeper into Gauss law and we can solve some more practical problems later. But before that, I have to introduce a technique. So for example, here, this ellipse shaped like surface area is called Gaussian surface, because it's the surface area we use to apply the Gauss law. And for every problem, there's not a natural Gaussian law for us to just use it. And we usually have to choose the surface by ourselves. And it's sometimes pretty tricky to choose an appropriate Gaussian surface. But with more practice, we'll eventually be able to choose fastly and accurately. So first, it has to be enclosed. So I already said that before. And then the second point is pretty interesting. It has to try to be either perpendicular or parallel to the electric field lines. So what does this mean? For example, back to the most simple one. If we have electric field like this, and then we want to choose a Gaussian surface, we want to be either perpendicular or parallel to the electric field lines. So the electric field is pointing right, so we can have a Gaussian surface like this in the first example. It is perfectly perpendicular to our electric field. So when it looks like this, when it looks like this, it means that the theta we mentioned above, actually didn't say theta, the theta. So we know that usually we should E times S times cosine theta, right? So when our surface area looks like this, theta equals to 0, and cosine theta equals to 1. And in this way, we can literally just cancel out cosine theta. So this makes our calculation a lot easier. And in another case, if we choose a parallel surface, this kind of means we choose a surface like this. The electric field lines just passes through the surface instead of intersecting with it. So in this case, theta equals to 90 degrees. So cosine theta equals to 0. And this also makes our life easy. So this electric flux equals to 0. It is easy to see because you see on this surface, electric field lines are all passing this way. No electric field lines passing through the surface. So the electric flux is of course 0. Okay. So let's do some example for practice. So this example 1 is 3 most basic and most used models for Gauss law. So we want to calculate the magnitude of electric field in the following situations. The first one says a point charge of Q distance r away. This is literally the same thing we mentioned above here. Hopefully you can do it by yourself later. And for question B, infinite long line charge with uniform linear density lambda and distance r away. So this, in case you don't know, this linear density lambda, this means lambda equals to Q over L. So it means how many charge are there in a unit length, in a unit for in a certain length. So for example, here's our line. And if we say we take a segment out, we say this part is H, then its net charge on this part is H times lambda, because lambda equals to Q over H, right? Okay, so that's the interpretation for question B. And for question C, it says an infinite surface with uniform areal density sigma. So this is pretty much the same concept as lambda. So sigma equals to Q over A instead of length. A means area. So similar. If this is a surface area, it has density surface areal density of sigma. That means if it have area of S, then area of A, then its net charge is A times lambda. Okay, so now that's all for so that's the introduction for this question, and you can think for yourself for a few seconds, for a few minutes. Okay, so I will start the calculation. We'll first do problem A. This is pretty simple. Actually, even if you don't apply Gauss law, you can do it, right? Because we all know the formula for a point charge r distance away, E equals to kq over r squared. But now we want to try to do it using we want to try to do it using Gauss law. So we draw a diagram. Positive q. Yeah, it emits electric field lines. Then we choose a Gaussian surface. We choose a Gaussian surface. So why we choose a sphere? Because for a sphere, every electric field lines is kind of perpendicular to our surface area. So that, like I said above, our calculation will be much more easier. Okay, so we write down our formula first. E times S equals to Q over epsilon 0. E, we want to know E, and S equals to 4 pi r squared. Q equals to Q, epsilon equals to epsilon. So E equals to Q over epsilon 0. We put this part here, 4 pi r squared. And 4 pi times epsilon 0 equals to 1 over k. So this simply equals to kq times r squared. So this proves our white formula in white, right? Okay, now we can do problem B. Problem B is a little bit more tricky. An infinite long line charge. So we draw a diagram still. It's really helpful to draw a diagram for Gauss law problem because you have to choose a Gaussian surface, and if you don't draw it, you might be confused by yourself. This is our line charge. And in order to apply Gauss law, we first have actually, in order to choose our Gaussian surface, first we have to know how the electric field lines distribute, right? So maybe some of you never saw a problem like this, like a line with charge. So can you imagine what its electric field lines will be? It is actually like a toilet brush. So I will draw it first, and later I can show you a 3D demonstration, which will be more intuitive. This is a 3D diagram. It's pretty hard to draw, but hopefully you can understand it. So it emits electric field lines all parallel to this surface, right? Like they're all horizontal, these electric field lines in blue. And it goes infinite because our line with charge is infinitely long. Okay, so now we know the distribution of electric field lines. Now we have to choose a Gaussian surface. So how to choose a Gaussian surface that is enclosed and is perpendicular to every single electric field lines? So if maybe some of you already thought about it, is we choose a cylinder. It is the best solution. We draw we draw a cylinder like this. This cylinder is our Gaussian surface. So why we choose this? So we have to say we will see this cylinder. It have surface area of top and bottom. So all electric field lines are basically parallel to these two top and bottom surface because they're all horizontal, right? So this means there's no electric field lines passing through our bottom area. And for the lateral side, every electric field lines so if we look from above, electric field lines look like this. Electric field lines look like this. And our cylinder looks like just like a circle. So it's similar to problem A. So you can see every electric field lines are perpendicular to our surface area. So this makes our life a lot easier. And in case some of you didn't fully understand this choice, I will show you a 3D demonstration. So here is our problem. This blue line over here, this blue line here is our line charge. It is infinitely long. Of course, I cannot draw it infinitely long, but you got the concept, right? And the electric field lines are the lines over here, are these lines with arrows, although not very well drawn. So they are all emitting from this line charge. It looks like this. And even at the place where my mouse is, there's still pattern like this. I just didn't draw it. So yeah, you see it actually looks really similar to a toilet brush. And for this cylinder, this orange cylinder is the Gaussian surface. It is enclosed, right? The enclosed Gaussian surface we choose. So you can see for the top and the bottom, no electric field lines intersect with, like, pass straight through, perpendicular to this, right? Everything is perpendicular. This line just goes through it, but didn't like pass through, poke a hole, So the electric flux for this orange top and bottom area is basically 0. And for our lateral side of our cylinder, now in orange, every electric field lines over here are perpendicular to our surface area. So our cosine theta equals to 1. So we don't have to consider theta anymore. Yeah, so this is an example of a perfectly chosen Gaussian surface because we can plug in our value very easily. And I will now do the calculations. Okay, so let's first write down our formula. E times S equals to Q over epsilon 0, right? E is what we want to know. And S, we already said that this top and bottom, we don't care about it. We only care about this lateral side. This lateral side of a cylinder equals to 2 pi r times H, right? And Q inside, well, Q inside, if we just say Q, because we do not really know, the problem gives us density, not Q. So we just said it's Q. And now we do some algebra. We put this whole thing to the right and combine. So this equals to 2 pi r epsilon 0. And we put Q over H together. Are you familiar with this? This thing equals to our linear density. It's the how many charge in a given length, right? So E equals to lambda over 2 pi r epsilon 0. Okay, so this is our result for question B. And now we'll move on to question C. Question C. Okay, so there's an infinite big surface. We still draw it. We cannot draw it infinite, but we just draw a surface, it would be fine. And again, in order to apply our law, we have to choose a surface, a Gaussian surface. And in order to know how to choose the surface, we have to know how the electric field lines distribute, right? So how is the electric field lines perform on an infinitely big surface with charge? And also it is uniform. This is also important. It is kind of have the same concept as speed. So due to symmetry, the electric field lines can only go perpendicularly up, vertically up, or vertically down. Also emitting from this surface, from this infinite surface. So why does this happen? Is if we say that there's an electric field lines, orange, that is kind of tilted. Is that possible? It seems possible, right? But it actually is not possible because our plane, our surface is infinite. If we have a line, so our surface is it's just a huge big surface. It is perfectly symmetry, right? If there's an electric field lines like orange, then why not there's electric field lines like this? And why not there's electric field lines like this? So this means due to symmetry, this orange thing can't happen because then there will be a contradiction between our theory. So all the electric field lines are perfectly vertical up or vertical down. And of course, there's not only one of these lines. There's this kind of line all over the surface. Okay, so now we know how our electric field lines distribute. So now we have to find an appropriate Gaussian surface. We still have the same law, so we have to make the surface enclosed, and it should try to be perfectly perpendicular or perfectly parallel to our electric field lines. So what can we choose? We can try a cylinder, right? Actually the same cylinder in problem B. We draw a cylinder. It's tilted, but it's actually not tilted. I mean, yeah, you got a concept, right? We draw a cylinder, and we can see for the top and the bottom area, these yellow electric field lines just poke a hole, like pass through this area, this blue area, right? So this means they are perpendicular. This blue area is perpendicular to our yellow lines. So cosine theta equals to 1. So these blue part are the areas that we have to consider. And for this time for the lateral side of our cylinder, electric field lines are all perfectly up or down. No electric field lines goes like this that pass through our orange area. So this means orange area has 0 electric flux, so we don't have to consider this area. So in case you didn't fully understand, I also made another 3D demonstration. Okay, so this is the huge infinite surface that have charge, and these arrows are all the electric field lines that go out of our surface area, like this. And also you can see not only the top of our area, there's this electric field lines. At the downside, there's also these electric field lines passing emitting out from our surface. Okay, so this, as you can see, this blue cylinder is what I said we can choose. So for the top and the bottom, these electric field lines perfectly poke a hole. It's perpendicular through this. So we have to, so theta equals to 0. So cosine theta equals to 1. We have to consider this two orange area when plugging in our formula, right? And then for our lateral side, don't care about that cube now. So for our lateral side in orange now, no electric field lines poke a hole through it. No electric field lines have any horizontal component. So this orange surface have 0 electric flux, and we don't have to consider it when plugging in our formula. So one important thing to note is that when we are plugging in our formula, we have two surface area, right? Top and the bottom. Sorry. We have two surface area, independent surface area, that both have electric field lines poking through it. So when we are calculating the E times S, that S have to be 2 times this single area, right? Okay, so also if we want, actually, we can also choose a surface like this cube. It basically have the same concept of with the cylinder. It's only their shape is different, and it can work in exactly the same way. And you can probably figure it out on your own. Okay, so now let's plug in the formula and do the calculation. So we write our formula. E times S equals to Q over epsilon 0. E is what we want to know, and S, we can just say that we don't want to plug in S. We just say this blue area equals to S, right? We just say like this. And then also it's the bottom. Here's also an S. Both have electric field lines passing through it. So our net surface, that's probably a weird way to call it. So our total surface area is 2S, right? Equals to Q over epsilon 0. What is Q? Q, if we just say Q is the net charge that are enclosed by our cylinder. So it's basically this cylinder area on the surface, Q. And again, if we do something interesting, we put this on to the right. This gives us right. So we got this formula, and also you are familiar with this expression. This expression basically equals to sigma. So we got E equals to sigma over 2 epsilon 0. So we found the result for problem C. Okay, so it seems that we are done with example 1. And hopefully, maybe you have noticed a very interesting pattern. So for problem A, this thing is proportion to 1 over r squared, right? And for question B, this expression is proportion to 1 over r. And for problem C, this E has nothing to do with r, right? Again, no r in this expression. So we can say it's perpendicular to r to the power of 0. So this is r to the power of -2, r to the power of -1. This is r to the power of 0. Okay, so this is just a pattern that is kind of interesting. So from a point to a line and to a surface, we have this pattern. And also, hopefully you notice that why this is independent to r. The E, the electric field, at here, or at here, or at here, they are basically the same because there's, for this expression, there's no any length variable inside. So why is this? Our electric field lines are all parallel with each other. They are all perfectly vertical, right? This means we got a uniform electric field. So in another way, and put this bigger, longer. If we say the electric field here, the electric field lines have a density of similar to this. And if we say the point here, the electric field lines, this density is still 2 lines over here. So we all know that the density of electric field lines represents electric field, the magnitude, right? So when its density is constant all over the space, so then its electric field, the magnitude of its electric field is also the same all over the place. Okay. So do you have any question about example 1? This is pretty important for Gauss law. Oh, okay. Or if you can ask at the end of the class, it's also fine. And example 2, I'm thinking we probably won't have enough time to do the whole example 2. So I decide to change example 2 into, we give a more specific thing, R. This R is smaller than capital R. So, okay, so let's read the problem. There's a sphere shell with charge Q1. Shell means it's a sphere, but basically it's hollow. It's like a ping pong ball. And then we want to find the magnitude of electric field in this space, distance r away from the center of the shell. And we now said that r is smaller than capital R. This means we want to calculate the point inside the shell, right? R is smaller than capital R, means it is inside the shell, inside the ping pong ball. So we draw a diagram again. This is our sphere shell. And in order to kind of be more realistic, I'll draw 2 circles because there's a shell. The shell looks like this. Okay, this is the center. And this shell contains a net charge of Q1. And now we want to calculate the electric field, for example, at this point, which is distance r away from the center. Okay, so let's apply Gauss law since our class is about Gauss law. What Gaussian surface should we choose for this problem? We still use the tips, right? We have to try to be perpendicular to the electric field lines. But we do not really know how the electric field lines distribute for a shell, unless you already done some similar problems, right? We want to know the electric field here, but we don't know. That's what the question asks. So we do not really know how the electric field lines distribute. But we can still choose an appropriate surface due to symmetry, because like the problem in one, there's a charge, then we choose a sphere. There's a point charge, we choose a sphere Gaussian surface. Then for a sphere shell, we can possibly also choose a sphere surface because it seems perfectly symmetric, right? So we choose a electric field. We choose a Gaussian surface as the yellow sphere, and then we plug in the formula. E is what we want to know. S is 4 pi r squared, the surface area of a sphere. And Q inside. What is Q inside? So the net charge inside this yellow sphere. Is there any charge? There's no charge, right? Actually, there's no charge because the problem says a sphere shell have the charge Q1. So all the charge are on the shell, are in the shell as yellow. I mean the red lines. These are where Q1 distribute. There's nothing inside the shell. So there's nothing inside here, nothing. So Q inside basically equals to 0. Nothing inside this yellow area sphere. This yellow thing is only, I mean, the center of the sphere. It doesn't mean any charge. Okay, so this means we plug in. Okay, now we got E equals to 0. Okay, so this is also a very, very important model. So for any shell-like thing with some whatever charge, whatever positive or negative or whatever, usually the electric field inside the shell always equals to 0, because you just simply draw a Gaussian surface. And you just simply draw a Gaussian surface and find there's nothing inside. So Q equals to 0 and E equals to 0. Okay. So now we can apply this to another simple model since there's still some time left. So hopefully we all know that here's two plates. This one with positive Q and this one with negative Q. Just a second. Okay. So here's positive Q and here's negative Q. And then we want to ask the charge, the electric field here. We kind of know that, maybe some of you know that everywhere inside a conductor, the electric field equals to 0, right? So we say electric field equals to 0. And now we can change the problem. We say here is a positive Q of it. plate. And here's a plate. We just connected with the ground and didn't do anything to it. And we just put it here. Then do you know how much charge is this? How much charge does it have? Actually, I already wrote the answer. It's negative Q, right? But why is it? It seems for our basic knowledge that this have to be negative Q, but we can prove it using Gauss law. So this time we're going to choose a Gaussian surface, which is still kind of weird, but you will eventually get used to it. We choose a Gaussian surface like this in the blue line. So this is the Gaussian surface we choose. You can interpret it as a cube or a square. It should be 3D, but for this problem, we just consider 2D, it will be fine. So we know that this electric field line is probably pointing this way. So we determine this part. Oh, okay, my bad. We determine this part first. It is perfectly parallel to our electric field lines in red, right? So this means its electric flux equals to 0 here. And then for the side, these blue lines of our Gaussian surface, we already know that everywhere inside a conductor, the electric field have to equals to 0. Electric field also equals to 0 here. So what does this mean? E times S equals to Q over epsilon 0. E times S, this is the total electric flux according to our surface area. Our chosen surface, this part have the electric field equals to 0. 0 times S. And this part, the green part, it is parallel to our red electric field. So it's equals to E times S times cosine 90 degree, which also equals to 0. So this whole thing equals to 0, equals to Q over epsilon 0. And this Q, I have to mention, it should be Q net. All the Q inside our chosen surface. So this means Q net equals to 0. This is important. So now we can get what Q is it here. So we know that this side has positive charge. And they have a net charge of positive. Have a net charge of positive Q. And then if we want the total charge inside our Gaussian surface equals to 0, as mentioned here. What charge have to be on the right side here? It should be negative Q. It should be negative Q, right? All here, everything is negative and has a net charge of negative Q. So that this Q net equals to positive Q plus negative Q equals to 0. So now we got our answer, right? This Q on the right plate, equals to negative Q. Right. Okay, so that's all for today's lesson. And 2 weeks later, I will give another lesson still on Gauss law, and we will talk about some more challenging and interesting problems. And hopefully it will help you more in electricity. And if you have any questions, please feel free to ask me. Okay, so I will assume that there's no more problems, no more questions. Okay. Okay, so thank you for listening and goodbye.